to address this, and I would like to address this. They are the same. Same idea. Same common concept. Okay. And then we can move on unless you have questions. So we are given a function f of x equals 3x to 2/3 minus 4. And we are specifically told this is the given interval. When we are given a closed interval for a function, we are asked to find everything we can about that function. And in this case, after we find the critical numbers, then we will discuss how we find whether those critical numbers change into a max-min or none of the above. A critical number does not have to become a max or a min. There are certain conditions that have to be fulfilled for a critical number to turn into a max-min. Okay, so first of all, I'm going to start my chart in which I put f prime first and f of x second. Feel free to invent your own chart if you would like to make adjustments to this one or use another chart. I'm fine. In the chart, I have the x values, and they have to be between -4 and 3. This is all we are discussing here. I have to find f prime because I'm trying to find critical numbers. So it's 3 times 2/3 times x to 2/3 minus 1. 2/3 minus 1 is -1/3. I will simplify 3 with 3. And what I have is this. X to -1/3 becomes 1 over x to 1/3, which becomes the cube root of x. Are we okay with this so far? Yes? We all agree? Okay. Now I'm asking you, does this function, I should say, f of x, of course, does it have critical numbers? And you should say, wait a minute, I know critical numbers come from two sources. Critical numbers come from f prime of x being 0, or from f prime of x being undefined when f of x is defined. So let's look at f prime of x, 2 over the cube root of x. Can this be 0? Why it cannot be 0? Because a fraction is 0 only if the top is 0. But can 2 be 0? Can I replace 2 by 0? No. So there is no critical number coming from f prime being 0. My next question is then, are there critical numbers coming from f prime being undefined? And the answer is what? X equals 0. So this is the only critical number this function has. Is 0 in the domain, in the chosen domain? Then I have to put it in. Careful. Under 0, for the derivative, I show that it's undefined. My next step, so far, what did I do? I determined the critical numbers. Now I want to go beyond that. I want to see whether this function, or I'm sorry, whether the critical number x equals 0 turns into a max or a min for this function. Okay. I need to study the sign of the first derivative here and here. So just please pick a number between -4 and 0 and plug it in, and just tell me the sign. Don't calculate anything. Just tell me the sign of this expression when you plug in x or replace x by a number between -4 and 0. Of course. And now plug in a number between 0 and 3, not 0 of course, in here, and tell me the sign. Don't calculate anything, I just need the sign of this. Positive. Do you all agree so far? Yes? Okay. Before we complete the chart and make a decision, I need to analyze something with you. So these are critical numbers and different situations. So 0 or undefined, 0, undefined, and I'm going to give you some situations and you will tell me what could the result be. Let's say when I have 0 or undefined, it doesn't matter. The difference for a critical number, it doesn't matter. If the derivative is 0 or the derivative is undefined, when it comes to the critical number, it's not important. So let's say I have this situation. Let's say I have this situation. Let's say I have this situation. And let's say I have this situation. So the derivative, this is the sign of the derivative. So imagine this is a critical number right here. I have it in my hand. This is a critical number, whatever, x equals 5. And on the right-hand side, the derivative, the slope of the tangent line to the graph is positive. On the left-hand side, it's positive. On the other side, on the right-hand side, the slope of the tangent line to the graph of this function is negative. What kind of point is this? It is a max. Because the tangent is positive, then the tangent is 0, and then the tangent is negative. What kind of point will that be? That's it. So this is the characteristic, this is the typical situation, or it could be undefined, it doesn't matter, for a maximum. It's definitely a local maximum. Will it be a global or absolute? I don't know yet. But it's definitely a local or relative maximum. Now let's look at the other scenario, the second scenario, second possibility. So I have the critical number right here in my hand. And the slope of the tangent line leading into it is negative. Then the slope of the tangent line getting out of it is positive. What type of point is this? Right. If the slope is negative and then is 0 and then the slope is positive, obviously this is a typical situation for a local min. Now I have a critical number. Here's in my hand. But the slope of the tangent line is always positive, or the slope of the tangent line is always negative. Is this a max or a min? No. So not only the fact that the critical number has to be right there, but if the signs of the derivative are not changing from positive to negative or from negative to positive, that critical number does not change into a max or a min. So this is nothing. It's not a max, it's not a min. This is nothing. Although there is a critical number there, it doesn't mean anything. Imagine x cubed. Okay, so here's x cubed, and then 0, and then going up. So this function is always increasing. I guarantee you that at 0, f prime is 0. But that is because the derivative doesn't change sign. That is not a point of min or max. Although the derivative is 0 at 0 for x cubed. So then, I'm coming back. We will make a decision in a moment. We will plug in the function x equals -4. We will plug in the function x equals 0. We will plug in the function 3, not all at the same time, of course, and I will determine these y values. So if you'd like to go to your graphing calculator, I thought I had it ready, but not. And punch in this function 3 times x to 2/3 minus 4. So in y equals 3 times x and caret in parentheses 2/3. Close the parenthesis. Close the parenthesis, please. What did just happen? Okay. Okay, -4. So now I go to second and table set. I have to reset the whole thing always. So second and table set. So I plug in -4, I plug in 0, and I plug in 3. So under -4, I will write 3.6 roughly. Under 0, I would write -4. And under 3, I would write 2.2. Okay. Before I look at these numbers, what should the function do when the derivative is negative? The derivative is negative. What should the function do? Decrease. Does it? Between 3.6 and -4, does this function decrease? Good. What should the function do now when the derivative is positive? Increase. From -4 to 2.2, does the function increase? Yes? From -4 to 2.2, does the function increase? Perfect. So now I have to make my decision. This is not a graph of the function. I'm just putting my y values so I can see them. So let's say 1, 2, 3, 1, 2, 3, 4. I'm not looking at anything right now. So other than, say, 3.6. So let's say 3. This is 3.6, height 3.6. This is at -4. And this is at 2.2. Again, I'm not graphing the function. I'm just plotting the heights. So the function at the leftmost point is here. Is somewhere is this value, -4. And somewhere else is 2.2. So what will I say about the point 3.6, -4, 3.6? As you see, I didn't even put them on the axis. I didn't even look at the x values. I don't care for that. What will you say about this point, -4, 3.6? Yes. Is it local? No, because it's at the end point of the interval. Is it global? Yes. So this point is a global max. What can you say about 0, -4, which is this point? What type? Local minimum, I agree, and also absolute or global, yes. So this point, 0, -4, local and absolute min. Excellent. Finally, what can you say about this point, 3, 2.2? What will I say about 3, 2.2? Nothing. By nothing, I mean no point of extrema. It's not a max, it's not a min, it's not local because it's at the end point of the interval. It's not a global. It could be only a global max or global min, but it cannot be global max because there is another one higher than it. It cannot be a global min because there is another one lower than it. So this point does not represent the point of extrema. That's how we study a function on a closed interval when it comes to its extrema, max, min, local, and global. I'm ready to look at another problem before we move on. So we can find the absolute max, min values of f on the given interval. Is this okay? Or we can choose another. Yes? Okay, so let's look at f of x equals 3x to the 5th minus 5x cubed minus 1 on the given interval -2, 2. Like before, I will get my chart going. I will use f prime of x first. I will put it first and then f of x. I have -2 to 2. So I'm asked to find the local max, absolute max, local relative min, everything about this function. So how do I start? What is my starting point? What do I have to do first? Yes, I have to find the derivative. So f prime of x equals 15x to the 4th minus 15x squared. Good. My next step, what am I looking for after I differentiate? I'm looking for the function, what? Why did I differentiate? Because I'm trying to find not yet. What will be my next step? I can get to positive or negative before I find its critical numbers. They come from two sources, but one of them is not possible here. Which one is not possible here? The undefined. It's polynomial. It's always defined. So all I have to do is write f prime of x equals 0, which will be 15x to the 4th minus 15x squared equals 0. Factor simplify, factor simplify. I will never divide by x, but I can divide by 15. Get it out of the way. And factor out x squared, but let me do it in 2 steps. So then x squared and x squared minus 1 equals 0. And then x squared times x minus 1, x plus 1 equals 0. How many solutions do I have to get? It depends on the degree. If the degree is 4, then I have exactly how many. They may repeat, but exactly how many and not more.
4.
Thank you, of course. Can anyone give us 4 solutions here?
0, 0, -1.
Good. Excellent. So now I'm back to my chart. I'm verifying whether all these are in the domain. If they're not, I have to disregard them. The domain is given to us, so I can change that. So it turns out that -1 is in the domain, 1 is in the domain, 0 is in the domain. So then I have -1, 0, and 1, 0, 0, 0 for the derivative. Now I'm ready to study its sign. So the derivative, one more time, f prime, I will factor out 15x squared. And just look at this, x plus 1, x minus 1. What type of number is this? Because I don't want to bother with it. If it's always positive, the sign will not be affected by it. So what type of number is 15x squared? Always. Always positive. So don't even, it does not come into play when we discuss the sign. Okay. So now, between -2 and -1, this will be a negative number, as well as this will be a negative number. So, because let's plug in -1.5. Negative, negative. So what will be the sign between -2 and -1 for the derivative? When I multiply 2 negatives. Very good. I'm going to plug in -0.5. -0.5 plus 1 is positive, but -0.5 minus 1 is negative. So what will be the sign of the derivative between -1 and 0? Is it negative? Yes? Now I plug in 0.5. With 0.5, this is positive, this is negative, so the sign continues to be negative. What about 1.5? Positive 1.5 minus 1 is positive, so I get positive. Now I will plug in the function all these 5 values, of course x. I will plug in the function -2, -1, 0, 1, and 2, and find these y coordinates. So I go back to the graphing calculator. I change y equals into 3x to the 5th, 3x to the 5th, minus 5x cubed, and then minus 1. And I go to second in table, and I want -2, -1, 0, 1, and 2. So I go back to my chart, and I will put these values in. So -57, yeah, I'll show you in a second. 1, oh yeah, I can switch it now, it actually doesn't matter. And then -1, and then -3, and then 55. I have to make sure that this row works well with this row. That's how I pick up on my mistakes. If this row is not in sync with this row, something is wrong. I have to go back to the drawing board. So what should the function do between -2 and -1? According to the sign of the first derivative. Is it increasing from -57 to 1? Correct. Now, what should the function do between -1 and 0 according to this sign of the first derivative? Right. Is it decreasing from 1 to -1? Correct. What should the function do when the first derivative is negative? Is it decreasing between -1 and -3? Perfect. Finally, what should the function do when the first derivative is positive? Is it increasing from -3 to 55? So then I know now that this row works perfectly with this row. Okay, finally, I'm just showing the heights so I don't make a mistake. Of course, you can use any method you like. So this is my -57, and this is my +1, and this is my -1, and this is my -3, and this is my +55. So what does -2, -57 represent? It cannot be local at the endpoint of the interval. It's never local. Global or absolute. So this is global min. What does -1, 1 represent? Excellent. Local max. What does a 0, -1 represent? Careful. The sign of the derivative does not change. Here it changed from positive to negative. It was a local max. Here it does not change. This is not a local max and not a local min. Nothing. When it comes to max min. Nothing. Okay, what about this one? 1, -3. Yes, the first derivative changes sign. So this must be a local min. Finally, 2, 55. What does 2, 55 represent? Exactly. This is an absolute max. This is how we go step by step to determine local max, local min, absolute max, absolute min, for a function given on a closed interval. Any questions? That's pretty much it that we have to discuss in 4.1. Any questions? Any questions? we have two theorems that are discussed in section 4.2. Oh, I'm sorry. Please erase the D and replace it with an N. Sorry. The mean value theorem. I don't know how I did not pick up on that. Sorry. Before we talk about the mean value theorem, prior to that, we have to discuss Rolle's theorem. Okay. So this is section 4.2, the mean value theorem. First, let's discuss Rolle theorem. Three conditions have to be fulfilled for Rolle's theorem. The first condition is a function is continuous on the closed interval a comma b. That's the first hypothesis. Second hypothesis, f is differentiable on at least the open interval. It doesn't have to be differentiable at the endpoints, but it has to be differentiable everywhere else. And the third hypothesis or condition, if you want, f evaluated at A must equal f evaluated at B. And you can say, but this is a special case. It is. It is. So let me show you a graph of such a situation, and then we'll draw the conclusion together. So here's the graph of a function on the interval a comma b. Here's the graph. This is one possibility. There are many different possibilities. Let me show you at least one more. And of course, you can find infinitely many examples. Let's see in both cases if the three conditions of the Rolle's theorem are fulfilled. Is this function continuous on the interval a comma b? When I drew it, I did not lift the marker off the paper. This is a continuous function. No gaps, no jumps, nothing. No holes in the graph, continuous. Yes. Is this function differentiable on a comma b? Remember, a differentiable function requires no cusps or corners, no discontinuities, and no vertical tangents. So no cusps or corners, no discontinuities, no infinite discontinuity or any type of discontinuity, and no vertical tangents. Both functions are differentiable everywhere between a and b. Let's check whether the third condition is fulfilled. Of course, I drew it like that. So here it is. So f of a equals f of b. F of a equals f of b. Okay, so now let's draw the conclusion together. Let's forget about the second option. So let's look at the simple first option. If a function is continuous and differentiable, like this one is, between a and b, there must be a point somewhere where f prime of c is 0. It must have a turn. And if it has a turn, f prime of that point has to be 0, right? So that's what Rolle's theorem says. Here it is. At this point C, how much is f prime of C? 0. So the conclusion is there exists a C in the interval a comma b such that f prime of C is
0.
That's it. With the second example, I want to show that there is at least one C. How many C's does this function have? A C1, a C2, and a C3. All of them are between A and B. It doesn't matter. So the theorem guarantees at least one, but it can have more than one. The function doesn't have to turn once, it can turn 5 times. So then you will have 5 C's. As long as these 3 conditions are fulfilled, because it has to come back to the same point, right? So let's look at a problem here. Find C guaranteed by Rolle's theorem for this function, and then find the same thing for this function. Let's choose one of them, or let's do both. With both. Okay, so let's see. We have f of x equals x to the third minus 4x on the interval 0, 2. I have to state all 3 hypotheses or conditions of the theorem. Number 1, is f continuous on the interval 0, 2? Why? The function is a polynomial. Yes, cubic, but polynomial. Since it is a poly. 2, f differentiable on 0, 2. True or false? Yes, since for the same reason. So it's a polynomial function. It's differentiable everywhere. Number 3, I have to show that f of 0 and f of 2 are the same value. If I cannot show that, I will have to say Rolle's theorem does not apply here. So how much is f of 0? Perfect. How much is f of 2? 0. Are all conditions fulfilled? Okay. So then I will be able to find a C between 0 and 2 such that what happens there? So f prime of C is 0. Perfect. I have to find f prime of x first. How much is f prime of x? Yes, minus 4. Good. So then f prime of C will be 3c squared minus 4. Then I have to create this equation in which I have 3c squared minus 4 equals 0, because I'm solving for C. Then I move forward, divide by 3. So c squared equals 4 over 3. How do I solve this equation? What do I have to do? Take the square root. Very good. I take the square root from both sides. So I have c equals plus or minus the square root of 4/3. At least one of these two numbers must be between 0 and 2. Which one I have to disregard for sure? Right. So c equals the square root of 4/3. And this is a number between 0 and 2. And I have to check. Of course, it's guaranteed by Rolle's theorem. Well, if all 3 conditions are fulfilled, I will find. So I have the square root of 4 over 3. So the square root 4 divided by 3. It must be a number between 0 and 2. And it is 1.155. So C approximately 1.155. Which gives a maximum or a minimum. I don't care what type. but it must have a turn. For a function to start at the same point and then come back at the same point, at the same height, in other words, the same y value, for a function that is continuous and differentiable, it must have a turn. It can have a turn being a maximum, or it can have a turn being a minimum. I don't know that. It may have several in between. This one only has one between 0 and 2. Any questions about Rolle's theorem? Let's also look at the other problem. So f of x equals 1 over x squared on the interval -1, 1. So we have the same question here. We're asked to find the c guaranteed by the Rolle's theorem. I cannot go ahead and do anything before I state the conditions of the theorem and make sure that those 3 conditions are fulfilled. If they are not fulfilled, or one of them is not fulfilled at least, Rolle's theorem does not apply here. So number 1, f continuous on -1, 1. Careful. It's 1 over x squared. This function doesn't even exist at 0. Can it be continuous between -1 and 1 if that does not even exist at 0? No. Rolle's theorem, not applicable. Rolle's theorem is not applicable here, because this function is not continuous on the interval -1, 1. It's undefined at 0. X cannot be 0. Okay? Any questions? Any questions? Based on Rolle's theorem, the mean value theorem was developed. A little bit more relaxed theorem. Okay. So let's talk about the mean value theorem. The first 2 conditions have to be fulfilled. No other conditions. The first 2 conditions from Rolle's theorem will be fulfilled here, but the third one doesn't have to. So it's not part of the mean value theorem. Number 1, f continuous on a comma b closed. 2, f differentiable on the interval a comma b. These are the only conditions for the mean value theorem. So here's the example now. So let's say I have this graph. Of course, this is A, this is B. This is the function f of x. So this is definitely f of b, and this is definitely f of a. And now I'm going to connect these 2 points with a line. So this is a line called, let's say, secant line AB. I know it's not the tangent, it has nothing to do with it. It's a secant line between A and B. And here's what I'm going to do next. I'm going to draw parallel lines to this line till I find a tangent to the graph. So assuming that this is my tangent, I'm a little bit off. Sorry about that. And this is point P. That's a tangent line at P. What can you tell me about the slope of these 2 lines? They must be the same, because we know that 2 lines that are parallel have to have the same slope. We agree with that. Yes? Can anyone give me the slope of this line? And then, of course, I'm going to ask you to give me the slope of this line. I'm going to say that this point has the x-coordinate c. So can anyone give us the slope of the secant line AB? Must be rise over run. Or what is the rise? It has nothing to do with calculus. So what is the rise? F of B, F of A. So this is the height, the rise over the run. Would you all agree with that? Y2 minus y1 over x2 minus x1. Perfect. Now I would like someone to give me the slope of this line, which is a tangent line, which has a lot to do with calculus. This one did not. So what is the slope of this line? Of? F prime of C. Excellent. And now what has to happen to these two slopes? Mandatory. They are equal to each other. So then F prime of C must equal F of B minus F of A over B minus A. And this is the mean value theorem. Of course, two conditions have to be fulfilled. The function has to be continuous and on the closed interval and has to be differentiable on the open interval. Then this will happen, for sure. C is guaranteed to be between A and B, and this will happen.
Don't we know that already?
No.
Well, I'm saying, like, when we learn some of those things, we that f prime of x is the same thing as the slope of f prime is the same as the slope of regular line.
We know that the slope of the tangent line is f prime of C. We know that the slope of a secant line is f of B minus f of A over B minus A. But now we are putting in two conditions. The function has to be continuous and differentiable.
Yeah, I was just wondering if we know that.
In a way we did. In a way we did. But with the use of the mean value theorem, we will be able to show whether equations have certain solutions or not. I'm not going to go into a lot of elaborate applications here, but it's a very important theorem, the mean value theorem. It's based on the Rolle's theorem, though, but it's more relaxed. It does not require and it does not show max min. It only shows that I can determine it's guaranteed, that C is guaranteed to exist for any function on a closed interval. Say it again, Thomas.
So this is more generalized.
It is more generalized than Rolle's theorem, yes, and it does not refer to a max or a min. Rolle's theorem was referring directly to a max min, which had to have a term. Otherwise, how will I get with a continuous function from this point to this point if it doesn't have a term? At least one. Good. So let's look at a couple of applications here. I know I have 20 minutes, I think. Find C guaranteed by the mean value theorem for f of x equals this on the interval 1, 3. So we're given f of x equals 5x squared minus 3x plus 1 on the interval 1, 3. So it says find the C that is guaranteed by the mean value theorem. What do I have to write first? F is? Yes. Is it continuous on 1, 3? The answer is yes, because this is what type of function? Polynomial, even quadratic, yes. as a Pauli function. Good. Number 2, is f differentiable? At least on the open interval 1, 3? For the same reason, because it's a polynomial function. Polynomial functions are continuous and differentiable everywhere. Okay, good. So now I have to find C. Find C in the open interval 1, 3, such that f prime of C equals f of B minus f of A over B minus A. So I have to find f of B, I have to find f of A, and I have to find f prime of X. So can anyone give us f prime of X?
10x minus 3.
Very good. Can anyone give us f of 1? So it's 5 plus 1 is 6. 6 minus 3, 3. Now I want f of 3. 5 times 9, 45, minus 9 plus 1. So 46 minus 9. Is it 37? Good. So now f prime of C. Can anyone give us this side? What should I write on the left-hand side? 10C, f prime of C. 10C minus 3. And then can anyone give us this side? Just dictate for everyone to see, and then we'll calculate. So f of 3, so it's B, f of 3, 37, minus f of A, which is f of 1, over 3 minus 1. So now in the past we knew that, but we didn't really determine C. Now we are able to, with the mean value theorem, we're able to determine C. Is that clear, Ian? It was a very good question. So 10C minus 3, 37 minus 3 is 34, 3 minus 1 is 2. So 10C minus 3 equals 17. So 10C equals 20, so C equals 2. Part B. We have the same. Any questions here? Any questions here? Same question for f of x equals 1 over x minus 1 squared for 2 intervals, 0 to 2 and 2 to 4. So we are asked to find 2 c's. Right. Which one? Right. The function is not continuous between 0 and 2. So the mean value theorem not applicable here. Perfect. So now let's look at 2, 4. 2 conditions have to be fulfilled. Is this rational function continuous on 2, 4? Yes, as a rational function. Defined there, yes.
Why is it not?
X minus 1 is 0 at 1. 1 minus 1 is in here, so it's not continuous. Defined there. And the same thing is differentiable on 2, 4 open for the same reason. It's a rational function defined there. So it's a rational function. If you remember from chapter 2, I'm quoting a theorem from chapter 2 that says the function is differentiable everywhere it's defined. And that's one of them is the rational function. But it's not differentiable, it's not continuous when it's not defined, which means at 1. Okay, so now this guarantees, and it will show us, we know now how to find that C. So f prime of c equals f of b minus f of a over b minus a. Have to find f prime of x first. I will change this into x minus 1 raised to negative 2. And then I will differentiate. I bring down negative 2, x minus 1 to negative 3 times the inner function prime, but that is 1. So then this is negative 2 over x minus 1 to the third. Are we in agreement so far? Yes? Everyone? Okay. So I have this part. This part is clear now. It's negative 2 over c minus 1 to the third. But now I have to work on this part and make it happen here on the right-hand side. How much is f of b? Which means f of 4. 4 minus 1 is 3. 3 squared is 9. So this is 1 over 9. Have to find f of 2. 2 minus 1 is 1. 1 squared is 1. So this is 1. So then the right-hand side is 1 over 9 minus 1 over 4 minus 2. Now I will be able to find c. And it's guaranteed to be a number between 2 and 4. Ready? Okay. So the left-hand side is negative 2 over c minus 1 cubed. Let's see what we get on the right-hand side. The denominator is 2. The least common denominator is 9. And this needs a 9. 1 minus 9 is negative 8. So now I have negative 2 over c minus 1 to the third. And this is, I copy the fraction from the top. And I flip, this is 2 over 1, I flip into 1 over 2. I will simplify. I will multiply both sides by negative 1. There are too many negatives in there. Both sides are negative. So then I have 2 over c minus 1 cubed equals 4 divided by 9. I will cross multiply. 4 c minus 1 to the third equals 18. I'll divide both sides by 4. C minus 1 to the third equals 9 halves. And of course, the cube root. There is only one answer, real answer. The cube root of 9 over 2. And I move 1. C equals 1 plus the cube root of 9 over 2. This number must be between 2 and 4. It's guaranteed. It's guaranteed by the mean value theorem. So 1 plus, in parentheses, 9 divided by 2, caret, parentheses, 1/3. You don't have to do it like this. So you can put it in the math, whatever. So I got that C is approximately 2.65. It's guaranteed to be between 2 and 4. The mean value theorem guarantees C to be between 2 and 4. Any questions? Should we do one more and then stop? I would like to get to these two on Wednesday, but should we do one more? Yes? Okay, very good. So let's look at last one for tonight. F of x equals the square root of x minus 4 on the interval 4, 13. We're asked the same thing. Find the C guaranteed by the mean value theorem. Where is my starting point? I'm kindly asking you to work on these problems. These are from the same handout with all your homework. work us on as many as possible from 4.1 and 4.2 so we can talk about them on Wednesday. Okay, so what is my starting point? I'm asked to use the mean value theorem, and I'm asked to find the C guaranteed by the mean value theorem. What do I have to do first? Say it again. Not for when I'm given the interval. So I start right away with f continuous. Because see, the interval, so x minus 4 has to be greater or equal to 0, so the domain is 4 to infinity. So it's a continuous function on 4 to 13. I'm quoting another theorem, the same theorem from chapter 2, in which we know all radical functions are continuous where they are defined as a radical. Number 2, f differentiable on the open interval 413 for the same thing. Now what do I have to write? I have to write the result of the mean value theorem. How do I write it? Can anyone dictate it?
It's f prime c.
F prime of c, f of b minus f of a over b minus a. Perfect. The left-hand side I have to differentiate first. So f prime of x, 1 over 2 the square root of x minus 4 times the inner function prime, which is 1. Then on this side, f of 13 and f of 4. How much is f of 13? Very good, 3. How much is f of 4? 0. So now can anyone create the equation that would eventually give us C? The left-hand side.
1 over 2
C minus 4. Good. Over. That's it. Perfect. That's all it is. Very good. So the left-hand side is 1 over 2 the square root of c minus 4. The right-hand side is 3 divided by 13 minus 4, which is 9, or 1/3. 1 divided by 2 the square root of c minus 4 equals 1/3. Two fractions are equal and they have the same numerator. What has to happen here for them to be equal? The two denominators have to be the same, or just cross multiply if you want, you'll get the same thing. So 2 the square root of c minus 4 must equal 3. This is a radical equation. I have to square both sides. Radical equation. So when I square 2, I get 4. When I square c minus 4, I get the square root of c minus 4, I get c minus 4. And when I square the right-hand side, I get 9. You can distribute if you want, or divide, whatever you want. 4c minus 16 equals 9. So 4c equals 25. c equals 25 over 4. This must be guaranteed in the interval 413. So 25 divided by 4 is a little bit more than 6. And 6 is between 4 and 13. And this was guaranteed by the mean value theorem. And these are two applications. As I promised, I'm stopping here. These are two applications other than what we just did by finding C guaranteed by the mean value theorem. These are two applications that help us prove something using the mean value theorem.
What would be a real world application?
I'm sorry?
What would be a real world application?
So these are, for example, show that the equation such and such has at most one root in the interval. That would be a real situation in which you would show using